Welcome, dynamic students. In this lecture, we're going to apply Eulers' second law and make the link between angular momentum of rigid bodies in planar motion to applied forces and moments, and also see how rigid bodies differ from particles or bodies considered just as points at their center of mass, for which we've already developed an angular momentum and relationship of this type in our particle kinetics section. So, we'll start with some definitions here, remembering we used Euler's first law to relate Newton's laws of motion to just the center of mass of a particle by integrating the mass and the velocity of that mass all over a rigid body, and then remembering that if it's a rigid body, the mass is the same. We later went on and said that same relationship would apply even to a non-rigid body. So now we're going to apply Euler's second law and look at our net moment, so our resultant moment, all the couples and all the forces acting at a radius from a given point to the change in angular momentum, our capital H. So we're going to, just stating Euler's second law, it says that the resultant moment about point O, and apologies for the smudge there, this is point O, so remember this is moment, so we have to be applying it at a point. That resultant or net or sum of the moments is going to equal the time rate of change of angular momentum of the rigid body with respect to that same point. So we have to be calculating with respect to the same point. And this resultant moment could be due to the sum of forces acting at a radius or couples or any mix thereof. So next thing, we just stated it, we haven't necessarily proven it, but we'll show a lot of strong relationships. So now we're going to look at how this relates to Euler's first law and linear momentum of a rigid body, in this case a rigid body, considered at its center of mass moving and forces moving it, and how that plays into our total expression for angular momentum of that body. So we're going to start out doing that by saying, okay, up here we looked at the time rate of change of momentum about point O, but let's use the expressions that we have already derived for angular momentum to look at that in terms of the angular momentum of that same rigid body with respect to just its center of mass, plus a radius from our point O of interest to the center of mass, vector cross product with the linear momentum of the rigid body. This was an expression that we derived when we derived expressions for total angular momentum of a rigid body in planar motion. So we've got kind of two terms here. One, angular momentum about the center of mass of the body, and the other, linear momentum and a vector going to a single place. This doesn't change with time. Unless body is moving, but it's a single number for the whole body because it's going to the center of mass of the body. And of course, our linear momentum can be represented by the momentum of a single point, a particle momentum acting at the center of mass. So we've got a term here, the angular momentum about the center of mass, which is very specific to a rigid body acting as a whole body. Then we've got another expression which is basically the equivalent to the time integral of r cross f, which is kind of more a point force application. So we've kind of got a rigid body part of our total angular momentum, and then we've got something that could be related to that same body acting at its center of mass like a particle. So we've kind of divided our angular momentum into those two sections. So if we want to relate this to applied total moment, the resultant moment, all we have to do is take the first time derivative according to Euler's second law. So the sum of the moments on that rigid body about some point O is the first time derivative of this angular momentum of the body around point O. So let's just take the time derivative. So we'll get the angular momentum at the center of mass, first time derivative, plus we'll have a derivative of a product, which will give us two terms. we'll have ROC dot cross L plus ROC cross L dot, UV plus VDU. So, or dVu plus duV, basically our derivative of a product. Make sure I said that right. As it turns out, this first term is 0, because when we take the first time derivative of our position vector from O to C, we get the velocity of point C, the center of mass in this case, with respect to our reference point O. So that's just V sub C, which is contained, it is really the vector part of our linear momentum of the center of mass of that body, which is just mv sub C. So we end up having V sub C crossed into something that's a scalar times V sub C, and because the cross product takes only the perpendicular portion of two vectors, we have something that is itself, if you're always parallel to yourself, so V sub C is parallel to V sub C, so the cross product of that term is 0, as we've stated over here. So that goes away, and we're just left with the sum of the moments being applied to this rigid body about some point O is equal to the time rate of change of angular momentum of that body about its own center of mass, plus the radius vector from our point that we're considering to the center of the mass of the body crossed into the time rate of change of linear momentum of the body, which can be taken as just the linear momentum of the body's center of mass as a point. If we wanted to write this in terms of the sum of the moments about the center of mass, all we have to do is use this property of moments. Basically, moment, the resultant moment about a different point is basically going to just be the first plus the radius vector to that second point, in this case from O to C, crossed into the force resultant. We're not saying anything at this point about couples. That certainly wouldn't change from any, if you had an applied couple acting on a rigid body, it wouldn't matter what point you were considering, that would not change. But if you had force resultants that were causing a moment, if we want to look at the moment around some point O versus the center of mass of the body, we have to include this second term to basically offset the distance of where the forces are acting. So if we substitute this term in for the resultant moment about point O and then rewrite this whole expression, we end up with an ROC cross L, L hat, because the sum of the forces is equal to the time rate of change of momentum by Euler's first law. So we end up just getting the resultant moment about the center of mass being equal to the time rate of change of angular momentum considered at the center of mass, which is really just, the simplest portion of this overall expression. So it's just that rigid body portion of the expression. So all we did was use some algebra and shift the point of rotation that we're considering, and then use definition of moment that we learned in statics to write this moment about a different point. Okay. So we can basically just use some algebra and substitution to write this same expression in a lot of different ways. If we consider the sum of the moments, resultant moments about any point, we can say that that's equivalent to the sum of the moments around the center of mass plus radius vector from that point to the center of mass crossed into the force resultant acting on the body. The force resultant acting on the body is, of course, equal to the time rate of change of linear momentum. The sum of the moments acting at the center of mass is equal to the time rate of change of momentum at the center of mass. And so these three expressions are basically all the same thing. Sum of the forces equals the time rate of change of linear momentum of the rigid body, which can be represented as its center of mass, which is equal to the mass of the body times the acceleration of its center of mass point. And in each case, because we're talking about angular momentum and moments, we would cross that term into our radius vector from our our point of interest to the center of mass. And then, of course, this stays the same. Time rate of change of angular momentum about the center of mass. Okay, now we want to dig into that time rate of change of angular momentum about the center of mass, because this is the wild card. It's a little bit difficult to get our head wrapped around. Maybe, how do I calculate that? It's a cool term, and it's something that's definitely new and unique to rigid bodies. But you know, if I have a rigid body, I'm like, okay, I know the sum of, I know the resultant moment. I've summed my moments, and I know what it is. And now I want to write an equation of motion, apply Euler's second law. How do I actually represent h sub c and its first time derivative? Well, in a previous lecture, when we started our section on rigid body planar kinematics, we defined the angular momentum of a rigid body in planar motion about its center of mass, about any point. But the center of mass expression was really easy. So I've rewritten that here. Remember, it is those inertial terms, the polar moment of inertia, I sub z, and then, in this case, I sub z going through point C, and then those products of inertia, xz and yz. So if we take the time derivative of this term that I just circled, then we can relate that to the sum of the moments by Euler's second law. Okay? The only problem is, in this case, if we take the first time derivative, we have a choice of what do we want changing. If we assume that our x, y, z is staying constant with time, it's the inertial reference frame, then because our moments of inertia are defined in terms of a distance that will be referenced to that, they'll be changing with time. And that makes it like very difficult to work with and to write any kind of easy to use expression for. So what we want is some way of taking the time derivative of our angular momentum such that our inertial properties stay constant, just like mass does in F equals ma in Newton's second law. Well, that means if these stay constant, then these unit vectors are going to have to change with time. You get one or the other. So what we're going to do is we're going to fix the properties, the inertial properties of the rigid body to a coordinate system that is fixed on the body, not the reference inertial frame wherever it is, usually outside the body, but it doesn't have to be. So let's go down and let's blow this figure up a little bit. This is a bit esoteric, but super important. Because remember, unit vectors change if we're talking about taking the time derivative of, in this case, of something with respect to an inertial reference frame. So we're going to define two sets of unit vectors. We've got an inertial reference frame out here with capital I and J unit vectors. So this is our non-accelerating, otherwise known as inertial reference frame out here. So that's the squiggly F inertial reference frame. So it has unit vectors capital I hat and capital J hat. So if we're going to take time derivatives, we need, and we're going to try to relate forces or moments to motion, we have to take derivatives with respect to that it's not itself accelerating reference frame. So we're going to be looking at the time derivatives of things with respect to capital I hat, J hat. We're going to define the inertial properties, our polar moment of inertia and our products of inertia of this body with respect to a little I hat, J hat on the body, so its own coordinate system. So the I hat, the moments of inertia are not going to change when we take the time derivative, because they stay fixed with respect to this I hat and J hat on the body, the little I hat, J hat. So they're fixed with respect to the body. But the little I hat, J hat, those will change because those now represent the actual motion of the body. And we used the same concept when we started initially looking at kinematics of rigid bodies and looking at a line at an angle with respect to a fixed reference frame and looking at the change of that angle with time as representing the motion of a whole body. So we're going back to that same concept. So we can define our little I hat and little j hat just with some trig to our big I hat, big j hat, with cosine and sine respectively. So we can just basically use theta and phi that are separated by 90 degrees and get those two expressions. And if we take the first time derivative of each of these expressions, we're of course going to get, in the case of, we'll go with little I hat, we're going to end up getting a negative sine theta, and of course, and then times theta dot. So we have to take the time derivative of what's inside the trig function. And then this big I hat doesn't change because we're taking that time derivative in the inertial reference frame, which is big I hat. So that one doesn't change. What we've done is change the little I hat relative to the big I hat and j hat. And so what we end up getting is this expression. Which, if you relate it to what we get from this expression, we get something similar to what we saw when we were deriving the relationships between the time rate of change of r hat and theta hat for cylindrical coordinates. We find that the time rate of change of little I hat is just the angular velocity times j hat, and the time rate of change of little j hat is the angular velocity of the body with respect to the inertial reference frame times little I hat. So we're going to use these two to basically represent I hat, little I hat dot and little j hat dot. And using those, so when we take the time derivative of this term and this term, we're going to end up, when we dot those two, we're going to end up invoking these. That will allow us to keep these terms as constant. And we don't have to do any kind of transform to represent k hat, little k hat to big k hat, because we have planar motion, so the z-axis is the same in our rotating, translating rigid body as it is in our inertial reference frame. So we can little k hat dot is the same as big k hat dot, so that's easy. So let's just substitute, let's take the time derivative of this expression using these two expressions for I hat dot and j hat dot and see what we get. So substituting in, we end up with our product of inertia being a constant, and we've got, we've taken, basically we have rephrase this. This is a product. Let me erase a little here to make it easier. We have a product. We have our omega, our angular velocity, and we have our I hat. So we've really got a three-way product here. So we've got a constant term, we have omega, and then we have little I hat, which will itself end up having a time derivative. So we're going to end up with two terms coming out of each one of these. We take derivatives. Well, we're going to have two coming out of the first two and only one out of the second. So we're going to end up with our first product of inertia times omega dot, which is now the angular acceleration, times in the direction of the little I hat, which is this direction on the body at that particular time, plus that same product of inertia times omega, just the angular velocity squared, because we had one, and now we've multiplied by this term, and now we're pointing in the j hat direction. We have the same analogous situation for the other product of inertia. in the YZ. And then the polar moment of inertia, the one that is with respect to the z-axis pointing out of the plane of motion, we didn't have to do any kind of crazy transform of the unit vector because, again, little k hat is the same as big K hat from the inertial reference frame, so it just ended up being our same polar moment of inertia times the first time derivative of the rigid body's angular velocity, omega hat. So if we group terms in the I hat and j hat direction, we can say the sum of the moments about the center, considered about the center of mass of the body, is equal to the sum of the moments about the center of mass in the x direction with the unit vector little I hat, plus sum of the moments about the center of mass in the y direction, j hat direction, plus the sum of the moments about the center of mass in the z direction. Now here's where we have our lovely simplifying factor where we don't have to consider products of inertia. If we have planar motion, we can't have any net moment in any direction other than the z direction, because if we did, we would start to move that rigid body out of the plane. We wouldn't have planar motion anymore. So the sum of the forces in the z hat direction has to be 0 because we're not moving the body out of the plane. It has to move only within the plane. And we can't twist it or rotate it such that it would no longer be in that same, moving in that same plane. So the terms that include all of our products of inertia have to be 0 by definition if we are restricting ourselves to planar motion. So we simplify our entire relationship between angular momentum and total net applied moment or resultant moment as for planar motion of a rigid body as just being the sum of the moments in the z direction about the center of mass is omega dot, which is known as alpha, and that is the second time derivative of the angle that the rigid body is making with like the x-axis or some reference line in the inertial reference frame. And time derivative of that angle is angular acceleration alpha. Then multiply by our polar moment of inertia and directed in a planar normal direction to the plane of motion. It can be pointing up or down, but it has to be perpendicular to that plane. So this is our rotational analog to F equals ma for a rigid body acting as a point at its center of mass. We can say the sum of the moments is the angular acceleration times the polar moment of inertia. So now we have a whole second term to use to describe the motion of the sum of forces and maybe couples, applied couples acting on a rigid body and its resultant motion. Because this angular acceleration can be part of our equations of motion. We've seen alpha many times in our kinematics expressions. So now we have a way to relate that alpha to something that we did in terms of applying a load or a force or a couple. So we're going to stop the lecture now, but then the final lecture in this chapter will go over several examples where we apply this. Basically, all of our long discussions of how we define angular momentum of a rigid body, how we relate it to the sum of moments, how angular momentum at the center of mass relates to angular momentum due to just the linear momentum of the center of mass of a body about some point. All of that is going to condense down into that sum of the moments around the center of mass equals alpha I, IZ. So that will be added to our force tally that we will use to get all the relevant accelerations. And once we have accelerations, we can write equations of motion. So stay tuned for that.